By 2030, global data center demand is expected to scale to nearly 1,000 terawatt-hours, heavily driven by AI workloads. That volume of power places acute physical strain on our existing high-voltage transmission lines. AI computing clusters regularly generate sudden, massive power spikes of up to 20 megawatts in sub-second intervals. Legacy grids are unequipped for this kind of volatility, resulting in interconnection queues that now stretch up to 10 years for new data centers. At the hardware level, the power density is staggering. Traditional servers require roughly 7 to 10 kilowatts of power per rack. Today, specialized arrays of AI graphics processing units routinely push 30 to over 100 kilowatts per rack. Faced with these hard physical limits, infrastructure developers are looking past highly saturated, temperate cities. They are planning to secure reliable energy by moving to two highly extreme off-grid frontiers. The energy crisis created by artificial intelligence can no longer be solved by incrementally upgrading existing electrical lines. The only path forward is to escape the traditional grid entirely. The first extreme frontier is low Earth orbit. Deploying high-capacity compute clusters as space data centers is a serious architectural proposal, building directly on the modular engineering of modern satellite megaconstellations. Placing data centers in specific sun-synchronous orbits provides one massive advantage: near-continuous exposure to raw solar radiation. This allows for massive, highly stable energy generation without any reliance on chemical batteries or terrestrial power grids. But operating in orbit introduces a severe bottleneck. Space is a vacuum. There is no air or fluid available to carry waste heat away from the silicon processors through normal convection. This curve illustrates the Stefan-Boltzmann law, the strict physical limit governing thermodynamics in space. It dictates that the only way to reject heat in a vacuum is by emitting infrared thermal radiation. To increase your cooling capacity, you have to drastically increase your physical surface area. If we apply this math to a single cluster of 400 AI GPUs, the hardware generates roughly 280 kilowatts of waste heat. Dissipating that thermal load requires 360 square meters of flat radiator panels, roughly the size of a tennis court, just to keep one cluster from melting. Scaling this architecture to a gigawatt-sized data center requires thousands of these panels. Lifting that volume of raw radiator mass out of Earth's gravity well pushes aerospace payloads and launch logistics far beyond current capabilities. However, lifting that much mass introduces a carbon paradox. Life cycle assessments show that over 70% of a space data center's carbon footprint comes from the production of the rockets and propellants themselves. To match the emissions of a terrestrial facility, we need a launch system 10 times more efficient than anything currently on the pad. While the orbital environment offers infinite solar energy generation, the strict laws of thermodynamics render the dissipation of gigawatt-scale heat both physically and economically untenable. The second extreme frontier targets the high latitudes of the subarctic. To secure firm, carbon-free baseload power, developers are exploring the deployment of small modular reactors, compact, factory-built nuclear plants installed directly behind the meter. This environment provides an infinite convective heat sink. By harnessing sub-zero ambient air alongside direct liquid cooling systems, operators can efficiently dissipate hundreds of megawatts of thermal energy. They achieve this without evaporating the millions of gallons of fresh water consumed annually by traditional data centers. The true hazard in the subarctic lies directly beneath the foundation. Co-locating multi-thousand-ton heat-emitting nuclear structures and hyper-dense data centers forces engineers to build on discontinuous permafrost, ice-rich soil highly sensitive to thermal disturbance. If thermal leakage from the reactor artificially deepens the active thaw layer of that ice, the soil instantly loses its load-bearing capacity. This triggers catastrophic differential settlement, physically tearing concrete basemats and deep pile foundations apart. This animation illustrates a passive thermal device, the two-phase closed thermosiphon. Angled pipes filled with working fluid intercept downward heat waves. The fluid absorbs this latent heat, vaporizes, and vents into the winter air, establishing a deeply frozen bedrock to permanently stabilize the facility. The subarctic environment effortlessly solves the specific thermal crisis of AI hardware, but it locks infrastructure developers into a perpetual civil engineering war against the Earth itself. For synchronous, consumer-facing applications, human perception research establishes a rigid limit. Users notice network latency at approximately the 100 millisecond threshold. The 100 millisecond latency budget must be distributed across sequential operations: outbound network transit, the model's prefill computation, the per-token decode, and return transit. The speed of light through fiber optic cables sets a floor, dictating how much budget physical geography consumes before processing even begins. Take a round-trip network request originating from a user in New York. The transit time is dictated by the physical distance the signal must travel. If we route that request to a server located in London, the round-trip network transit alone consumes 70 milliseconds of the budget. This leaves only 30 milliseconds to process the complex model prefill and decode the initial output tokens, a time frame that is currently technologically unfeasible. If developers deploy infrastructure to remote locations based solely on access to power, without accounting for the physics of data transmission, they risk delivering a degraded customer experience. Terrestrial cables conform to challenging topographies and pass through optical amplifiers and regional switching nodes, each adding microsecond processing delays to the total journey. If an inference request originates from a user in a financial center like London and is routed to a subarctic facility, that long-haul terrestrial routing consumes 40 to 80 milliseconds round trip. This leaves the inference server with insufficient time to process the model prefill. Despite unlimited power and efficient cooling, subarctic data centers suffer from the same latency penalty as space data centers for real-time interaction. To manage infrastructure effectively, enterprise strategy must move away from monolithic deployments. Operators must adopt workload segmentation based on strict latency profiling. First, real-time synchronous models, such as voice agents and interactive coding assistants, must be retained strictly within urban colocation zones. To operate within urban power limits, these facilities must use smaller, quantized models paired with continuous batching to guarantee delivery within the 100 millisecond budget. Second, as AI moves towards autonomous reasoning, power-hungry agentic workflows and batch generation tasks must be offloaded to subarctic nuclear facilities. This works because 75% of enterprise workloads are latency tolerant. An 80 millisecond network delay has no measurable impact on a multi-step reasoning task that takes 30 minutes to compute. Shifting these asynchronous tasks to subarctic zones provides access to cheap compute while preserving urban grids for critical real-time processing. Finally, capital for space data centers must be confined to aerospace, defense, and global logistics for space-native intelligence. The primary application for this is Earth observation and radar analysis, where event-driven inference is executed directly in orbit. Using a method called change detection, the onboard AI analyzes raw sensor data, discards the unchanged baseline imagery, and downlinks only the critical insights. By discarding irrelevant data in orbit, operators reduce communication volume and bypass ground station delays, achieving near-instantaneous situational awareness. The future of inference infrastructure requires precision. The enterprise that maps its software workloads to the unique physical, thermal, and economic properties of the urban edge, the subarctic tundra, and low Earth orbit will secure a decisive operational advantage.